Hey AP Chemsters, this is Mrs. Vanderwall bringing you the 18.8 edition of Blank Wall. What is happening here is what if the reaction as written is non-spontaneous? What if the E value is negative, delta G is positive, K is less than 1? How do we deal with this? And this is really through like what electroplating is all about. How can you force something to go the opposite direction? Well, what you need is a battery. You need some source of power to force the voltage to go the opposite direction. So the oxidation will still occur at the anode, the reduction still occurs at the cathode, and so the battery flow is forcing it to go this way. So things that don't typically want to be oxidized can now be oxidized if you have an external battery. Okay, so that's what's going on over here. Again, the anode is your positive, your cathode is your negative, same as before. Now, in your pictures, usually we have like a little voltmeter here. In the past, we showed you these spontaneous reactions. This is the symbol that symbolizes your battery. Okay, and so electroplating, a lot of things can be electroplated. Zinc is a very common thing. It's called galvanizing if you electroplate zinc onto things. So you're depositing a neutral metal atom on the electrode by reducing the metal ions. So again, at the anode, that is the piece of the plating metal. So that's sort of like my zinc bar would be if I want to zinc plate something else. The cathode is the object to be plated. So if I want a spoon or something in my picture, it looks like a spoon, to be plated, maybe I want a silver plated. That sounds kind of fancy, and maybe rich people have silver plated spoons. So you stick a silver bar here as your source of silver ions, forcing the electricity to go this way. Now on the spoon has where all the negative electrons are going to be deposited on the surface of this spoon. So the positive silver ions from the bar will be attracted to the negatively charged spoon and will play it out. So your silver ion will be reduced onto that spoon, and apparently that's what you want to do if you want silver plated spoons. Okay, let's see the next page. Here is another situation that you don't see every day, and that is forcing water to make hydrogen gas and oxygen gas. Normally it's the other way around. So if you think of the Hindenburg, that was the big blimp filled with hydrogen gas. All it needed was a little bit of a spark, and boom, it easily was converted from the two gases into water vapor. But what if we want to go the other way around? What if we have a lot of water, but we want to make hydrogen and oxygen gas? How do you force it to go into the non-spontaneous process? Well, you need a battery to that. You need some kind of a electric source to force it go to that direction. Okay, so what if I have a mixture of ions that I need to plate out? So which one would be plated first? Well, here I have cerium, this VO, and this iron 3+. So if I look at my chart, actually the chart that's in your book doesn't have cerium in it. I looked, but I did look it up, and cerium is listed as 1.70 as a reduction. This VO2+ is on your chart at 1.00, and let's use iron 3+ going to iron 2+, so the voltage is 0.77. So it says, give the order of oxidizing ability. In other words, which ones are most easily reduced of these species, and predict the one which will be reduced at the cathode at the lowest voltage. And there you go, right there. So if you look and think about this, which one is most easily reduced is the one with the highest voltage. It's the one highest positive voltage, I should say. So that's the one that's going to be most likely to be reduced. Okay. This next thing is huge, all right? So if you were to star one thing, I would star this, okay? This is what your lab is going to be about. We're going to be actually electroplating brass keys and whatnot, going through this process, okay? So you're going to have to do this math as part of your lab write-up. So it says the stoichiometry of electrolytic processes, or, hey, factor label. That's how I go through it. That's how I see this, as just a factor labeling process. And it all depends on what you're given, and all depends on what you want. Okay, so if you look at the example down here, all right, how long must a current of 5 amps, well, what the heck is an amp? An amp is a coulomb per second, be applied to a solution of silver plus ions to produce 10.5 grams of silver. So what's asking here? Let's go back to this question. Here, I'm silver plating my spoon here. So what if I needed 10.5 grams of silver on this particular spoon? All right, my battery has certain amp, 5.00 amperage. How long is it going to take me to go through this process? So that's what this question down here is asking. So there's a lot of information here, and again, I would factor label. So how long must a current of 5 amps be applied to a solution of silver plus ions to produce 10 grams? All right, so what I would do first is start factor labeling. Okay, so what do I know first? All right, I need to find how many seconds. Why seconds? Why not minutes? Why not, hours? Because of this right here. It's coulomb per second. So your time factor is going to be in seconds. Now, what was our given amount? Looks like I have 10.5 grams, it's periodic table, oh, I'm going to need that, of silver. Okay, so obviously I don't want grams. Grams has nothing to do with it, so I'm going to go to the mole. That's what you always do with grams. When else, or what other kind of a thing would you not convert to moles? Probably some thermochemistry, but that's really about it. So 1 mole of silver is like 106? Let me look. 107.9, sorry, 107.9 grams of silver. Okay, now how does this help me? Well, what am I looking for? Okay, I have coulombs. Right here's coulombs. What kind of a unit is a coulomb? Well, let's kind of check this out. So convert the quantity of charge in coulombs to moles of electrons. So there is a relationship between coulombs and moles of electrons. Well, I can also convert moles of electrons to moles of acetylens. How many electrons will silver lose? All right, so I'm going to do this over here. Okay, oops, sorry, left out something. Here we go. And so if I have 1 mole of silver, how many moles of electrons? Well, do that equation. So here's silver plus what? 1 electron will get you silver. So your moles of electrons are 1. That's kind of handy. If it were zinc, it would be +2. If it's aluminum, it'd be a 3. Okay, that's not too bad. And then what? See that mole of electrons? I'm going to get rid of it. I'm going to factor label it out. So I have to keep going. I ran out of room here. So there's my coulombs. Coulombs is moles of electrons. So it was 96,000. Oh dear, what was that number again? I'm looking up 96,485. Aren't you glad they gave you that on the equation sheet? Otherwise I'd be up a creek. And then finally the current, all right, is 5.00 amps. And here we go. We have need to get rid of those coulombs, and I do that with the amps. So it says it is 5 coulombs in 1 second. It is just factor. Don't worry, we'll practice another one, but that is the relationship. So you need moles of silver, you need moles of electrons, you need to convert moles of electrons to coulombs, and then your amps will convert you to time. So voltage was joules per second. Your amps are coulombs per second. So think about what you're given, and what do you need? Do you need volts or do you need amps? Well, here you need your amps to finish out the seconds. So go ahead and do your math. So it's not too hard. 10.5 divided by 107. That's almost 0.1, isn't it? All right, and then times this 96,000, and then divided by 5. And I think if you're doing your work, I think you get roughly that many seconds. And to me that makes sense because this is about 100,000. 100,000 divided by 5 is 20,000. 20,000 times 0.1, which is 0.1 here, is about 2,000. So that makes a lot of sense to me. It works. Okay. Why 3 sig figs? Because this is 3 sig figs and the 5.00 was 3 sig figs. So that's why I get 1880 seconds. Okay. Let's go on. Okay, so I'm not really sure why this is in here. It doesn't really ask you to do anything with current or time or math or whatever. This is in, I think, in the wrong section. I think it should have been in 18.5, not 18.6, or even, yeah, sounds good. So I'm going to skip this to save you time because you've already done these, right? And that's good here. So what's next? I want to look at an AP problem. How about you? This came straight off of an old AP exam, and let's see how this helps us, okay, what we just talked about. So it says an external direct current power supply. Well, what does that really mean? So using our language, that's your battery. An external direct current power supply is your battery. It's connected to 2 platinum electrodes immersed in a beaker containing some copper sulfate, as shown in a diagram above. Sounds good. As the cell operates, copper metal is deposited. So you are doing this. You are going from copper 2+ to copper metal. And then what? Oxygen is produced. So that's your O2 bubbles right there. The 2 reduction half reactions are listed below. Now, think about what's going on. This works. All right, that's your copper going to copper 2+. But look at this. I am making oxygen. I am not using oxygen. So this is my reduction. So this is my oxidation. And when I flip that number around, I get negative 1.23 volts and 0.34 positive 0.34 volts. And so my overall E value is going to be negative, which tells me what? It is non-spontaneous, and that's why you need the battery. Okay, so it says on the diagram indicate the direction of the electron flow. So it still goes from anode to cathode. So it's going to go this direction. Okay. Now what? Predict the net ionic equation. All right, we can do that. So I need to scroll down. I need a little more room here. So I have Cu, that's a Cu, 2+ plus 2 electrons going to copper. That's my reduction. And then I have my H2O liquid. It's a liquid. Going to, I need to scroll up here. Actually, no, I don't. Going to O2 gas plus 4H plus 4 electrons. Now, again, what do I have to do? I have to multiply that by 2. So then my net reaction then is going to be 2Cu2 plus 2 H2O. It's a 2 there, making 2Cu plus O2 plus 4H plus. Okay, so there is my net ionic. Now what? Predict the algebraic sign of delta G, justify your prediction. Well, what do you think is going to happen? So if my E value is negative, what do you think delta G is? Is that positive? Yes, it is. All right, so it's a positive value. Why? Because it is not spontaneous. Now it says calculate the delta G for this reaction. All right, we can do this. So look at your equation and what relates delta G and the E value. So delta G is equal to negative NFE. Okay, which is equal to negative, well, what's my N? How many electrons are being transferred? It ends up being 4 because you had to multiply this by 2. So that's your 4 right there. And then this is your 96,000, what is it, 96,485. and this is coulombs per mole. And then my E value, let's go back up. I never did subtract out, did I? So we have negative 1.23 plus 0.34. And that's negative 0.89. So that's my E value. So times negative 0.89. And what's my unit? Joules per coulomb. That's why I need the volts there, because it's joules per coulomb. So now if I'm going to multiply all that, hey, what happens to my negatives? They are going to cancel. Times 96,485, and I got, how many sig figs? 2 sig figs. It looks like, this is what I got with 2 sig figs, which is, oops, okay, that's nothing. So it's 340 kilojoules. What's the sign? Positive. Okay, so it's 340. Now what? It says electric current. Oh, this is the current stuff. All right. Now, electric current is 1.5 amps, passes through a cell for 40 minutes. Calculate the mass of the copper. So let's factor label. So I need how many grams of copper is equal to, well, what's given? 40 minutes. And what is a coulomb, or what's an amp? I'm sorry, coulombs per what? Coulombs per second. All right, so I need to convert minutes to seconds. And now I need to convert seconds to coulombs. All right, and what is that value? Okay, that is my 1.5. This is my amp. Now, how would you know this? If you look on your equation sheet, you will see the I equals Q over T. Do you see that? It's right underneath the negative NFE. So I is current, Q is charge in coulombs, and T is time in seconds. So there's your 1.5. Make this look more like a 1.5. So it's all there on your equation sheet. And now, hopefully, the rest of it will turn out. I got coulombs down here. What is your Faraday's constant? It's coulombs per mole. So I'm going to put mole up here. And this is your 96,485. I'm going to have that memorized soon, aren't I? But now I got to keep going. 1 mole of electrons. Oh, I should put the E over here, huh? All right. And now what? Well, look at your copper. How many moles of electrons are you using, all right, in this whole thing? It's not just the copper, it's the whole equation. So it was that 4 electrons, like what we had here and here in the earlier one. So that was part B. We saw that it was 4 electrons. So I'm going to put 4 moles of electrons here. I'm sorry. 4 moles of electrons down here. And what am I trying to do? Trying to find the mass in grams. So I need to erase what I just did. All right, right here. Ooh, I'll just do it again. So it was your, what, 4 moles of electrons. All right, for 2 moles of copper. Why? Because I'm looking at that equation again where I had 2 moles of copper, that balanced equation. 1 mole of copper is 63.55 grams. Periodic table. So why don't you pause this and come up with an answer? So I don't know about you, we have, looks like 3 sig figs, so I got 1.19 grams of copper. Okay, now look at the next one. Calculate the dry volume in liters measured at 25 degrees C at 1.16 ATMs of the oxygen that is produced. Well, I'm thinking of Pivner. All right, you're looking for volume. All right, you have temperature, you have pressure. What's the only thing missing? You're missing moles. All right, so if you will bear with me, I'm going to erase some of this. All right, Mrs. Vandewall, why are you erasing this? Because you're going to see it's almost the same problem up until the very end. Okay, so I can stop right here and now go back to that balanced equation that we had. So 4 moles of electrons gave us 1 mole of oxygen. So if I make this 1 mole of oxygen, oopsies, here we go, 1 mole of oxygen, That's all I need to do. All right, why is it? Because I'm going to be using Pivnert to then fill out the rest. Okay, so if you do your all your work and you leave at the divided by 4, then what do we get? We get 0.0096, nope, sorry, 936, sorry about that, moles of oxygen. And now I'm sure you can put this in your Pivnert expression. I won't bore you through that. So go ahead and do your Pivnert. Please do your work. But when you're done, volume is equal to 0.197 liters. Okay, so again, how did I get through E and F? I did it by factor labeling, and all my units are given to you on that equation sheet. So I know it seems like a lot of factor labeling, and truly it is, but don't get lost. Your units are going to cancel out. So I am done with these notes. I know we have a couple more practice problems still left in your packet, but we'll save that for later. So take care and don't wait to be great. Bye.